Hi, I'm Sunjay, and I'm here to talk about how Spectre breaks cryptography and what we're doing about it. Let me show you what I mean. This code is from libsodium, a well-known crypto library, and this is one of the encryption functions. This code has been formally verified to be constant time, which means it shouldn't leak your secret information to an attacker. This code will leak your secret information to an attacker. And it's because of Spectre. So I'll get to how this happens, but first I need to explain constant time. And to explain constant time, I need to explain side channels. So let's get started. Here's a snippet of naively written crypto code. Super simple, 2 lines long, looks totally reasonable. On the surface, all it's doing is a substitution table lookup. This is a component of AES encryption and other algorithms. In particular here, it loads a byte B from secret key, then uses B to look up a value from table. It's not obvious, but just this little snippet of code leaks the secret key to an attacker. And it's because under the hood, when the processor loads table of B from memory, it brings it into the cache, so that the next time something uses table of B, it won't have to go all the way out to memory. It just pulls it from the cache. But this means table of B, for whatever value of B we just used, is going to be a lot faster than table of any other value. So if an attacker accesses every entry in table and measures how long each one takes, they can infer the value of B, which is a byte from the secret key. This is a cache side channel, and it's just one of the many side channels an attacker can use to learn secrets from crypto code. So how do we prevent these side channel leaks? We use constant time programming. So what exactly are constant time programs? Well, the name is a bit of a misnomer, but what it refers to nowadays are programs where both control flow and memory accesses are not influenced by sensitive information. This second point in particular, if you prohibit secret data from influencing memory addresses, like array indices or table lookups, then secret data can't make it into the cache state. So even if an attacker probes the cache, they can't get anything useful. This is why constant time works really well. Just a few simple rules that you can statically verify, and it guarantees your program won't leak any secrets. Except it completely fails to account for how processors actually process instructions. Modern pipelined processors fetch instructions ahead of time and have multiple instructions going in flight all the time. So if this is your program, then by the time the processor is finishing executing an instruction here, it's already fetched and started working on all the instructions down through here. But when it gets to a branch, the processor needs to know where to fetch the next instructions from, but it doesn't actually know the outcome of the branch condition yet. So it'll rely on a branch predictor, which will guess which branch the processor should follow. If the predictor guessed correctly, then the processor already fetched instructions on the correct path and everything's great. But if it was incorrect, if it mispredicted, then the processor has to roll back, throw away all the stuff it did here on the incorrect path, and restart on the correct one. But as far as the program itself is concerned, nothing bad has happened since all the wrong computation was thrown away. But is that really the case? It's not the case. Stuff like cache state isn't reset. Let me show you. Say we have this code, and most of the time n is within bounds. Then public A of n is loaded into x, which is then used to index into public B. Nothing in this code touches secret data, so it's trivially constant time. There's nothing to leak. But what if at some point n happens to be really big? Well, since most of the time this condition was true, the processor will predict that this is still the case, and start executing inside the branch. But now public A of n is an out-of-bounds memory access. Depending on n, it can load anything in memory, including this encryption key stored over here. And this gets stored into x. Then when x is used as an index, this secret value from the encryption key makes its way into the cache state. At this point, the processor might finish calculating the branch and realize that it mispredicted, and it rolls back and resets to here like it was supposed to. But the really big problem, like I told you earlier, is that the cache state is not reset. And so the encryption key still gets leaked through the cache. And it's from execution that never even should have happened. Speculative execution just lets you straight up ignore control flow checks because of branch misprediction. And this is why standard constant time models just aren't enough. So if we want to reason about Spectre attacks and defenses, we need to bring constant time to the speculative domain. And so this is what we did. We created a formal semantics for speculative execution. We created a new notion of speculative constant time in terms of our semantics. We created a static analysis tool for detecting speculative constant time violations based on our semantics. I'll go over these in detail the rest of this talk. Let's start with the semantics. So if we want to formally reason about security during speculative execution, we need to formally model speculative execution. And if we want our model to be useful, we need to be abstract over processors and hardware details. We need to capture all the different forms of speculation and prediction, and we need it to be amenable to security proofs. So first off, like I said, we want our semantics to be abstract over any microarchitectural details. We don't want to have to worry about what specific hardware a program might be running on. So our semantics models a general multi-stage pipeline processor, and we keep track of a reorder buffer, which holds the set of transient or in-flight instructions. And at each semantic step, we can fetch the next instruction from memory into the reorder buffer, we can execute an instruction anywhere in the ROB, or we can retire the oldest instruction in the buffer if it's fully resolved. So how do we know what action we're going to perform each step? Well, in practice, a motivated attacker can influence or control the execution on a processor. So we're going to assume the attacker supplies a schedule of directives. And at each step, we take the next directive in the schedule to determine what we're going to do, whether that's fetch, execute, or retire. So next, what about speculation? Just like a real processor, when we fetch a branch instruction, we need to know which path to fetch further instructions from. And so our solution here is, once again, the attacker directives. So anytime a step requires prediction, like when we're fetching a branch instruction, the attacker supplies the outcome through the directives. For example, this directive, fetch guess true, will fetch the branch instruction and will also predict that the condition will be true. So finally, we want to use the semantics to reason about the side channel security of programs. Like here, when we execute this load instruction, we want to capture that it leaks its address. So we just make that explicit. And again, just like with everything else in our semantics, we keep these observations general. Memory operations leak their addresses, and control flow operations leak their jump targets. And so this way we don't have to deal with the specifics of things like cache replacement policies or register port contention. At this point, I can show you exactly how our semantics capture Spectre attacks. Here's the example from before, trivially constant time, but susceptible to Spectre. In our semantics, the program will look something like this. And let's suppose this is the schedule of directives. So according to the schedule, we first fetch the branch into our reorder buffer, and we're going to speculate that the branch is taken. Fetch true. We'll store all of this information in the buffer since it'll be useful later. We also fetch the next two instructions inside the branch. So when we execute index 2, because n is out of bounds, we end up loading this secret value as the transient value of x. Then when we execute index 3, we use that transient value of x, the secret value. So the actual value we load is garbage, but the point is the address that gets leaked by this load instruction includes the secret value. And so now an attacker can read this from the cache state. Eventually, when we execute index 1, we realize we misspeculated and we roll back and take the other branch, but the leakage has already been observed. Again, even though this program is sequentially constant time, we can show with our semantics that it's insecure under speculative execution. In this talk, I've only been focusing on branch prediction, but our full semantics captures a variety of prediction mechanisms. In addition, we also model fence instructions which block speculation and are used in many Spectre mitigations. So now that we have these semantics, we can define what it means to be speculatively constant time. The sequential statement of constant time is that sensitive data shouldn't influence anything observable to an attacker, so control flow and memory accesses need to be independent of secrets. Our speculative constant time statement builds on top of that. Secret data shouldn't influence anything observable to an attacker, regardless of the schedule of directives given by the attacker. So even if they have full control over the schedule and over the predictors, they still shouldn't be able to learn any secret information. So now that we have this security property, we can check programs for potential Spectre attacks. We built a static analysis tool, Pitchfork, which symbolically executes a binary using a subset of our semantics. So we point it at a function, tell it which parameters are secret, and it'll go and flag any instructions that are leaking secret data. When we analyze a program, we give Pitchfork a speculation window, which roughly corresponds to the speculation depth of a real processor, how far down a wrong path it can misspeculate before it's forced to roll back. The speculation window in Pitchfork limits the number of entries in the reorder buffer, so if it's full, we're forced to retire instructions before we can fetch new ones. With this speculation window, Pitchfork traverses the program along a set of worst-case schedules. If the program would have any speculative constant time violations, then at least one of Pitchfork's schedules will have a secret leakage. You can find the proof of soundness in our full paper. We ran Pitchfork on functions from several popular crypto libraries and found speculative constant time violations in both the libsodium and OpenSSL libraries. The vulnerable libsodium code is the same code I put up at the very beginning of this presentation, but now I can actually show you what's going on. So like I said, all of the code that you see here on the screen, including all of the function calls, have been verified to be constant time. But there's more code that you don't see, and that's because libsodium is compiled with stack protection to prevent stack smashing attacks. So the compiler inserts this little bit of assembly right at the end of the function. So all this does is check if the return address has been tampered with. But because this stack check is a conditional statement, an attacker can force it to mispredict. So this stack check fail function prints some messages to standard error using a printf-like function called libcmessage. And as part of the string formatting it does, libcmessage traverses a linked list. So this for loop is a conditional branch, and an attacker can cause it to speculate beyond its intended range. So then, speculatively, we'll run off the end of the linked list, and now we have arbitrary memory access that gets leaked through pointer dereference. So as you can see, Pitchfork is able to find speculative leaks in real crypto libraries. And since it analyzes binaries, it can find leaks, like in the libsodium case, that source-level checkers would totally miss. In summary, we developed a framework for reasoning about Spectre attacks and defenses. Specifically, we created a semantics for speculative execution, we formalized the notion of speculative constant time, and we built a binary static analysis tool that finds violations of this property in real code. And that's a wrap. Thanks for listening to this talk.